Hello everyone, and welcome to the technical video for our Senior Design 2 project. Our team name is technically W3, but usually we just go by Team Power Glove. In this video we aim to show off our project and its functions and also explain the three subsystems that make up the project. And this video will cover these three subsystems to a great degree of technical detail. Our final project consists first of a hardware component, which is essentially a glove covered in various sensors which allow us to capture the wrist movement through space, as well as the bending in the fingers and thumbs and the spreading in the fingers and thumb. This data is then sent down a pipeline in which we are able to unpack it and use it in the software Unity. Once in Unity, the data is interpreted and is used to move a graphical representation of the user's hand. The same sensor data is then put into a machine learning algorithm which is able to detect if the user is making any of the ASL signs 0 through 9 or if they're making none of those signs. The motivation behind this project was to provide a sort of 3D immersive environment in which we are able to accurately detect the hand. And this could be used in any sort of application where state detection of the hand is necessary. I think VR is one that comes to mind. The deaf and mute community or anyone who uses the American Sign Language system could probably benefit from something like this. And then lastly, there's also the personal learning that we were able to get from working on this project. This project had a few aspects of it that various members of the groups wanted to get better at. And I think that we all learned a lot throughout the process of building this device. Introducing all of our team members, we had 2 electrical engineering students, me and Travis, and 3 computer engineering students, Tom, Dakota, and Duncan. And for roles, it was pretty spread across software, serial communication, and hardware. Travis worked a lot on the software and serial communication side. I worked mostly on hardware and serial communication. Duncan was kind of involved in all three, but mostly hardware and serial communication, because although he was computer engineering, he was the one who actually assembled the glove and put it all together. And then Tom was heavily involved in software, because he was online only, and Dakota supported Tom on the software side as well as putting a lot of work into the serial communication system.
To detect the bending of the joints, we used a 2-inch flexible sensor from Spectra Symbol placed on both the MCP and PIP joints of each finger. The Spectra Symbol flex sensor ranges from about 25 kiloohms when unbent to 100 kiloohms when bent. Each sensor is connected to a 22 kiloohm resistor used in a voltage divider configuration. To detect the spread of the fingers, we use an A1308 linear Hall effect sensor with an accompanying neodymium D51 magnet, which is 5/16 by 1/16 inch. The magnet has to be in line with the sensor in order to detect properly. If the Hall effect sensor leaves the perpendicular plane of the magnetic field, it is no different than the sensor being very far away. The range of this sensor is about 1.5 centimeters. To detect the wrist movement, we use the onboard IMU on the Arduino Nano 33BLE. The accelerometer and gyroscope are implemented together using a complementary filter. The gyroscope is very precise but tends to drift, and the accelerometer is a bit unstable but does not drift. The complementary filter gives us a pretty accurate representation of the angle of the hand. Since we needed 14 analog pins, we had to use 2 Arduinos. We use them in a slave to master hierarchy, where the Arduino Every is the master and the Arduino 33BLE is the slave. We use multiple 8-bit messages to send the information from the slave to the master. Because the Arduino Nano every only has one serial port, we had to use a different option when communicating between the master and slave. The serial software library allows the digital pins to be used as serial ports.
The master Arduino collects all data so that it can handle sending glove sensor data to the PC that is running Unity. All data is converted into a JSON object. This allowed us to define a flexible class structure that could be sent as a string through the serial port. JSON objects are transmitted via the serial port at a baud rate of 115,200 bits per second. Each value is mapped to a property with the length of a single character to reduce payload size. This increased the speed at which we were able to deserialize objects on Unity from roughly 25 to 40 objects, resulting in a much smoother virtual representation of the hand. Once the JSON object is received by Unity, our script deserializes the JSON string into a defined C# class. This C# class had each JSON property mapped to one of its own. We were also able to use more descriptive property names once deserialized so that it would be easier to pass the sensor data further down the pipeline to their correct functions.
Our second subsystem is a virtual simulation of the hand in Unity engine. The hand model used is provided in the Leap Motion development kit for Unity. The hand is made up of nodes in a parent-child hierarchy, where every child's local position is relative to its parent. This hierarchy is shown on the left of the screen, and you can see where each node corresponding to a joint is positioned within the index finger chain as I click through it. Because every child's local position is relative to its parent, we are able to rotate joints individually in a forward kinematic way to animate the hand. Forward kinematics is the method of calculating end position from a list of known angle or joint parameters. As I rotate the index finger at the MCP joint, you can see that nodes further down the chain move with it as if it were a single rigid object. Bending at the PIP joint shows the same effect, and its angle is preserved when I continue to rotate the MCP. To animate the hand in software, we use the transform.rotate function. This function takes three parameters: the axis to rotate around, the angle in degrees to rotate, and whether the axis is interpreted in local or world coordinates. Because the angle for each joint will come from the glove data, the only work we have left is to find the vector for rotation. For the interphalangeal joints, the blue axis is represented by the local space forward vector. This can be used in the rotate function to bend the IP joints. Since the glove only has one flex sensor on the top of the fingers, the same angle will be written to both the DIP and PIP joints. At the MCP joints, the local green axis, or the up vector, can be used to spread the fingers. As the fingers spread, the direction of the local forward vector changes as well, resulting in unnatural converging of the fingertips as they are bent at the MCP joint. To get around this, we can instead use the direction of the forward vector at the wrist's local space to bend the fingers down, regardless of orientation. Since the Hall effect sensors used to detect finger spreading only function up to a certain distance, when a finger is bent, both the finger and the fingers next to it will be set to a zero spread angle. Thumb opposition is achieved by rotating the thumb at the CMC joint in the directions defined at the wrist. To pull the thumb out, we rotate in the wrist's forward direction. To rotate the thumb to face the palm, we rotate in the wrist's right direction. And to move the thumb across the palm,